All right, so we left off with this circuit that we had yet to figure out which current induced this voltage source here. We need to determine that, and then we need to determine the polarity of those sources before we can solve this circuit. Okay, so let's do that now. So first, let's take this coil number 2, because we know that this is the coil whose current induces the voltage in this, or the current through the second coil here. It's going to induce this voltage source that we're going to use in our model to solve the circuit, okay? So I2 is the current that's flowing into the dotted terminal of the second coil. So for the sake of the dot convention, let's just keep it consistent. Let's say that the current flowing into the dotted terminal is the current that's going to induce this voltage source, okay? So I have I2 flowing in, and I have I1 flowing this way. Or I have I2 flowing here, and I have I1 flowing here. So based on KCL at this node, the current flowing into the dotted terminal is I2 minus I1. So let's call this I2 minus I1, the current that's inducing this voltage source, okay? And so in terms of polarity, let's go ahead and summon our trusty statement about the dot convention here. I'll just go ahead and put that down here. Positive current into the dotted terminal 1 forces a positive current out of the dotted terminal of the other. Okay, so let's take a look here. In this circuit, I have I1 flowing into the dotted terminal of the first coil, which means I'm going to push a current out of the dotted terminal of the second coil. Okay, so if I want to push a current out of this, I need current flowing in this direction. That means I need my voltage polarity to look like this. So let's go ahead and draw it just like that. And the same goes for the other coil. I have current flowing into the dot here, I2 minus I1. We just determined that. And so if that's the current that's flowing into the dot here, I know I need to push a current out of the dot here. And so if I want to push a current out of the dot here, I need a voltage polarity that looks like this. So let's go with this voltage polarity here. And now we're ready to solve the circuit. Let's go ahead and put our pluses and minuses in here. Plus, minus, plus, minus. Obviously for the voltage source, it's already good to go. Plus, minus on this side. And then over here, it's going to be plus, minus across this guy and plus, minus here. And so we're pretty much ready now. Oops. We're pretty much ready now to solve this circuit. Now we can just write our two loop expressions. We're basically going to end up with two equations and three unknowns, but then we're going to plug in values for M. Ultimately, what we're after is the average power dissipated in this resistor here, and we can determine that using our average power equations from the last module. Okay, so let's just try and start by determining these two currents, and then once we have our currents, we can find the average power. So let's grab this circuit and take it with us over to the next slide. Just put it here. And let's go with our first loop here. So our first loop, we're going to go 30 angle 60 minus I1 times, and now we have a series of impedances here. 5 plus J 3.77. Okay, then we voltage drop, right? We're dropping voltage across this source, plus to minus. So we're going to write minus I2 minus I1 times J 120 pi M. Now we voltage drop across this source, or this impedance here, and it's going to be I1 minus I2, right? That's the current flowing through that impedance. So we're going to write minus I1 minus I2 times J 11.31. I know this is insane. This problem is pretty tough, I would say, but that's why we're going through it. And then lastly, we go across this voltage source and we're raising the voltage. We're going from a negative to a positive, so we're going up in voltage, and we're going to go plus I1 times J 120 pi times M. And that whole thing is going to be equal to 0, okay? So that's my first loop. Oh my gosh, I'm writing horrible zeros. There we go. That's my first loop expression. Let's write an expression for the second loop. Starting here, we'll just go this way. So we're dropping voltage across this source. So I'll write minus I1 times J times 120 pi times M. Then I go across the J 11.31 impedance. That's going to be voltage drop. And I have a current I2 minus I1 flowing there times J 11.31. And then I just have minus I2 times 10 ohms. Gives me 0. Okay, so I've got everything in terms of I1, I2, and M now. And what we basically need to do is just solve this horrible algebra for I1 and I2 so that we can get expression for I2 in terms of M. And then we can plug in our 3 values of M here that were given and determine the average power for each. Okay, so I am not thinking it's a good idea for me to sit here and do all this algebra on screen. I will do it, but I don't want to do it on screen because it's going to take a minute. So I'm going to do it. I'll make sure I don't make any mistakes, and then I'll just jump right ahead to that. And it'll definitely be published in the slides when I post them. But I don't want to waste your time as I sit here and crunch through this algebra. So I'm going to go ahead and solve it, and then I'll come back when I've got expressions for I1 and I2 in terms of them. Okay, so I'm going to go ahead and end this video here, and we'll see you guys in the next video.